Learning Outcome 4.1. Describe how and why Fourier transforms and Fourier series are related. Recall from Chapter 3, you were introduced to the Fourier series and the synthesis equation for it. You were also introduced to the analysis equation. We're going to look at an example that ties in what you learned about the analysis equation to help you learn about the Fourier series. We're going to consider this rectangular pulse train. It was on the table of common Fourier series that you had from Chapter 3. It was signal number 6, and the A0 and A sub k were provided for you. Those values, using a height of 1 and a rectangular width of 1, produce an A0 of 1 over T0 and an AK of 1 over T0 sinc of k times omega naught, which is 2 pi over your period, divided by 2. These are right from your table. Check out how I got those. So let's take an example. If we have a width of 1 and our T0 is 8, this top window shows you a picture of your time signal, x of t. It repeats every 8 units and has a width of 1 and a height of 1. Your A sub k magnitudes are the sinc function. Remember, these are magnitudes. Magnitudes are always positive. So your sinc function that used to be negative, coming down and having a negative periodic decaying pulse, all those negative loops are going to be positive now. The phase, wherever things were negative, is going to be 180 degrees, or pi, and that's 3.14. So you can see where it should have been negative by the phase being pi. Now what happens if we increase our period of 8 up to 16? Think about what your time signal is going to look like. And you can flip back in the video. The spacing between our pulses just got bigger. And what's happening to the amplitude of our A sub k? It got smaller. What else do you notice? Going between your A sub k when t is 8 and your A sub k when t is 16. You should see that these lines are closer together because your omega is k times omega naught, and omega naught is 2 pi over t naught. T naught's bigger, so omega naught is smaller. So your omega naught is your spacing, and that just got smaller. Otherwise, the shape is the same. Still a sinc function, which would have gone negative. But we're plotting a magnitude, so it's positive. Okay, I'm going to increase t again. 32. What'd you see? Amplitude decreased. Spacing is omega naught, and omega naught got smaller. T is 64. Your pulses are further apart. Your A sub k got smaller. And your line spacing is a lot tighter. Well, this doesn't get to be very interesting, because if I keep increasing our t value, our A sub k's are just going to go to 0. So instead of looking at A sub k, we're going to look at t times our A sub k. We're going to take that period and bring it over to the other side of the equation. So now our period times our A naught will be a constant value of 1, not affected by our t. Likewise, our t times our AK will be a sinc, and the amplitude of that is not going to change either. So let's do the same set of experiments. T is 8, time signal, t times A sub k, and our angle A sub k. As t increases, we can see the spacing between our pulses increasing, and the spacing between our a sub k values decreasing. But this time, the amplitude of our sinc function did not change. So now when t goes from 16 to 32, spacing still bigger, spacing still smaller, amplitude is the same. T is 64, spacing is bigger, spacing between our samples is smaller, amplitude is the same. If t goes to infinity, what is our exit t going to look like? What is our t times our a sub k going to look like? What is our angle a sub k going to look like? Pause the video and think about it. Don't continue until you have a guess. Well, if our period is infinite, the spacing between this and the next sample is going to be infinitely big. That means it's just one of these. While technically it's periodic, with a period of infinity, in reality it's not periodic. We only have one, because infinity is an awful long ways away. The spacing between our samples, our 2 pi over t naught, is our omega naught, and our omega naught is 0. So our spacing between points is nothing, epsilon. That means we now have a continuous plot. And our phase is still going to look the same way, compensating for the fact we don't plot negatives if we're plotting magnitudes. And our amplitude stays up here at 1 because we have our t times our a naught. Now let's look at the equations. From our Fourier series, we have an analysis equation and a synthesis equation. Fourier transforms, which is now the topic of chapter 4.1. Fourier transform handles the cases where we have aperiodic signals, signals that are not periodic. And that will have an analysis equation and a synthesis equation very similar to what we had for Fourier series. So let's compare them side to side. What do we see? What's similar? What's different? Pause the video and compare the two and think about it. Well, this 1 over t is missing, but we explained that because that t got brought to the other side. That's why that's not there. And we're going to call that t times our a sub k. We're going to call that x to j omega. That's the name we give to a Fourier transform. We usually write it with a capital letter, and the j is there just as a general convention. It really is just a function of omega. We're integrating over one period. How big is our period? Goes from minus infinity to infinity, so we're doing the same thing there. X to t, e to the negative j, k times omega naught. We saw all through chapter 3 that k times omega naught is omega. That's no different. T dt, t dt. They look pretty similar. Synthesis equation. We're summing from k's negative infinity to infinity, and we just change to an integral. Well, if omega is continuous, summation becomes an integral. That makes sense. Our a sub k is what we had from our analysis equation, and that became x to j omega. So our a sub k is going to become an x to j omega. E to the j k omega 0, e to the j omega is k times omega naught. There's our t. We have a d omega now. And because we had that t going the other side, and omega is 2 pi divided by t, we've got this d omega, and we have this 1 over 2 pi. Again, Fourier transforms work for aperiodic signals. Fourier series work for periodic signals. But in general, they work very, very similar. And I hope that everything you learned in chapter 3 about Fourier series, you can now take and hold on to it and use it with Fourier transforms. We'll have lots of examples, lots of problems, but this should get you going.